Hey everyone, welcome back to the channel. Today we're going to be looking at a little piece of software I wrote that lets you take a bunch of different images and stitch them together into one big one where they actually all kind of line up to where they should be in the actual, if you took just a larger focus image. The way this is done is with what's called Orb and a lot of Homography Transforms. So I want to show you what the final result's going to look like. So basically what we're going to do is we're going to take these little images I took of my room, it's just the background back here. You see I've got our nice little canvas painting back there, which offers really good kind of unique features to detect. And I just kind of made sure that I took images that had some overlap. So if you see between this image and that image, you can grab all the bottom of these guys, and the next one, it's going to keep all of that in frame. So you can keep moving, but you got to keep some of it in line, and then just ran all the way through. And from there, what we're going to do is we're actually going to produce a final image that's going to look like this. So you can see it actually did stitch them all together and produce what would be the image if you had just been able to take a step back and get everything in frame at the same time. So with that being said, let's get into the code. Alright, so let's get into the code. So the first thing you're going to want to do is download all your libraries. The two main ones we need are Computer Vision and NumPy. You're also going to use the OS library, which is going to just let you do access to the folder structures. The main thing to do is just to install these with pip. If you don't already have them, you can use the requirements.txt that is in the repo, which there'll be a link in the description. Otherwise, just install these two commands. Once you have that, the next thing you want to do is decide what your final image size is. Now, this is really dependent upon both how many images you're going to be using and in how much area you're trying to cover. For me, I just did an 8 little image sample here, so I kept it pretty small. Minimum number of matches needed. This is kind of the core of the project here. So if you go down here, what we're doing is we're actually doing the Orb Detection. So Orb Detection is this really cool software that was based on, I think, Sift and Surf, which were proprietary for a while there. And then Orb became the open source version of them, which is essentially saying, okay, I've got two images with, I know has commonality between the two. Orb lets you actually find individual pixels and their relationship to other pixels and say, oh, well, I found them in this image as well. So once you find that, okay, I've got maybe someone's face in this photo and the same face is in this photo, but that's actually been moved to maybe down and to the right, I can use Orb to actually detect that. So Orb is going to be able to come in and say, okay, well, your transformation matrix actually looks like this. And that transformation matrix is what you would do to multiply this image, like the pixels and orientation, to get it to match this image. So it's really powerful, and it's using a lot of like pose estimate. So in robotics, one of the projects people will use this for is if you want to do visual odometry. So visual odometry is when you've got a camera that you have mapped to a robot and you want that robot to actually map the environment. Well, the way it's typically done is might be with a LiDAR, or you've got basically something that's producing a 360 view of your room, and you continuously match points to that. Well, you can also do it with a camera if you just have a single, it doesn't even have to be a depth camera, just a single camera that is pointing at a wall with maybe some slightly more unique textures to it rather than just like a flat painted matte wall. That's a little hard for it. But if you've got individual like items, or maybe you've got a bunch of paintings hung up, it's going to do a really good job of saying, okay, between frames, here's those same objects and what's the transformation between the two. So it lets you build the environment as you go. So this is kind of a introductory to that kind of algorithm used for a completely different project, but similar concepts. The query directory, this is just where we're going to store all our images. So whatever images you decide to take, you need to keep them all into a separate folder. For me, I've called it images. And then they need a very specific naming pattern. I just kept it with the two numbers, so image 01, image 02, etc., all the way down to your final image. Basically, the reason for this is because we're kind of cheating with this program. We're giving it a baseline homography like transformation off of the initial image and values that we hard code. So from there, it builds from image 1 down to image 2 down to image 3. So like image 1, it's going to map initially to just the final output image, but then image 2 is going to find the commonality between image 1. So it's going to see a lot of this, probably see some in the corner of the painting, and it's going to figure out how to map that onto the initial one. But it needs to know what that central, like the set point, the stake was. So moving down, what we got here is we just make a little display window. So it's not super needed, but this in OpenCV has a really cool functionality that lets you basically construct a dynamic view image. If you've use like imshow, that's just going to show up the image whatever size it is. But if you do it with the create window, or rather a named window, you can actually better control its sizing and positioning stuff. So nothing crazy here. We give it a max size that will allow it to fit on the screen, and then from there it'll start to scale down. Basically, if you try to run this on a smaller screen, like maybe you wrote this on your desktop with the ultra wide like I am, and then you go to desk or a laptop, you want to make sure that it scales properly and doesn't just, fall off the screen. So this right here, calculate homography transform, this is kind of like the bulk of the project. So at this step, you've already found matches using Orb, but you need to now find the transformation matrix. The transformation matrix is what basically takes the relationship between the two matches and says, okay, here's how you make this image overlay with this image, or this one overlay with this. The transformation matrix is kind of fundamental for a lot of robotics and a lot of computer vision, so it's very important to get a good concept of that. But this function here is what lets us take the orb information out of the orb create and the orb detect and actually get a transformation matrix out. Specifically, we're going to get a homography matrix, which is basically just going to incorporate how you do that kind of shearing and scaling from one image down to the other. If we look through this quickly, there's really not a lot to it, and there's a lot more information out there from computer vision, from OpenCV's kind of wikis that I highly recommend you just look at there if you've got questions, because they run through every parameter. There's a lot more you can do to kind of tune this. Basically what I say is I want to give it a minimum number of matches. I don't want to allow, Orb Detect can sometimes say, okay, I found a max of however many features you give it. For us, we give it 3,500, but it can also find a minimum of 0. That isn't going to do very well, and you actually aren't going to do very well with something maybe less than like 10 matches. So for me, I gave it 20. It said it needed to have at least 20 matches to actually produce a transformation matrix. Any less than that, I found that the images started to get a little too distorted, or they didn't quite line up really well. It's very important to get a higher number of matches to help really solidify its information about where that image is supposed to lay. Up to a point, it's useful. At a certain point, if you're saying the difference between 1,000 and 2,000 matches, you're probably not going to see any change. So you don't want to set this value too high. If this does occur, we're just going to return early, and it's going to keep going with the next image. Right here, you've got the source points and destination points. So this is just saying I've got the matches, or rather the pixels from image 1, and I want to map them to image 2. I think in reality, actually, it's the other way around. I think we go from the second one down to the first one, where this is the source, this is the destination, because we want to map this image down to this one to get it onto the final overlay. And then from there, we just call the actual built-in CV function find homography. So this takes in your 2 points, like the 2 lists of points. We've redimensioned them to, or reshaped them rather, to feed into this function properly. Basically, if you look at this function, they're going to list you through all the different options you have. You've got a bunch of parameters you can feed into it. Specifically, the ones you may want to tweak is your methodology, along with your threshold. So we're using a process called ransack. Ransack is this very fast methodology of kind of finding, doing the math on this. What it does have as a trade-off is sometimes you can lose some accuracy. So if you want to play with some different results and try some different functions, that's how you do it. There's, I think, like 3 or 4 built in. Yeah, and you can read all about the pros and cons of those on OpenCV's site. That's really cool information. I find it very informative, so I highly recommend you dive into it if it's something you really want to understand more than just a surface level of how this is being done. From there, we just return the matrix. Obviously, Python's really great about just being able to return anything, so just throwing it out there. Find homography also returns, I forgot what else its actual return is, but it's not needed, so we just throw it away right there with the underscore. Then we've got this function called detect feature. So this is the function that actually occurs prior to this calc homography transform. This is the one that will actually find the matches between 2 images. So you pass it in the images, and you could also give the option to show like the actual feature match. For me, I just defaulted to false. I only do that when I was debugging this project. It's not super useful when unless you're actually displaying each image at a time. When you have a huge folder of images, it gets unwieldy. It's not worth it. Basically, the first thing you gotta do is make a detector. The detector is just saying, okay, I want you to use the orb algorithm. You could have done this with SIF and SURF. I believe at this point they're now available to not be, I don't think they're patented or copyrighted anymore, but the Orb one is the one I've always used, and it's open source, so you might as well go for it. You want to pass in number of features. Number of features is how many matches it's going to try to produce. Basically, it's going to break that image down into a bunch of different subsections and then try to match there. So I like to give this a pretty high number. I think 3,500 is probably overkill. In fact, I know it is. But if you've got the compute power, I like to just throw a bunch at it, because what we're going to do, remember, is we're going to filter down a lot more for only the top like 10% of matches. So we're basically going to say, okay, find 35 matches, but we're only going to grab like the top 10% of ones that we think are really, really solid, or rather the detector really thinks is solid. From there, I'm just turning the image into grayscale, the source image. That's nothing fancy. And then I actually run detect and compute. So detect and compute is going to give me the key points and descriptors. So key points are the actual pixel XY coordinates, and the descriptors carry with them a bunch of other basically meta information that we can use to say almost a ranking on the classification of how good these actually are. Mask is just an unused parameter. It's basically just to say you could actually kind of be a little more specific in your matching there. And then I pass in the source image. Nothing crazy there. This function, honestly, in computer vision and robotics, if you're going to be doing a lot with that, you'll probably use these 3 lines hundreds of times. I know I've used several projects in robotics, specifically with doing like SLAM, where these 3 lines of code are my favorite thing I've ever been added to computer vision, because it's so easy. You do it and you're like, wow, that's immediate. And then, okay, so moving down, we've got this is where I was telling you about how we had to kind of cheat with getting the first image mapped onto the overall final big image. What we did here is you just took 4 of your coordinate points and mapped them to the new spot. So source points are your initial image's size and positions. Honestly, a lot of this is just trial and error. Starting at the top left, I went 0 and mapped it to the top left of the new image. Then I took my farthest right image, where I actually opened up my image and kind of mapped over and saw how many pixels it was, what its width was. And then I mapped it to the subsection of the final image. Did the same thing with there. You can see basically my rule of thumb was I just did a 1/10 on each one of these. And so what I did is just took top left, top right, bottom left, bottom right, and just keep mapping them over all the way to like a very small section of the final image. From there, what you do is you cheat and you say that's the source points and ortho points. This is the equivalent of up here. We did our source points and destination points. And we find a homography transform that will actually get us that new mapping. So it's going to do the scaling and the shear and the rotation. And I return out the actual image that we originally had fed in. So right here we read from the source directory and then image 001. So we read this one. And then we just feed it in and we return the transformation matrix. The fuse color images, this is kind of one of the trickier parts. So basically what's going to happen is you're going to get a mapping after this program is done of all your images. So for me, it's these 9 images, or rather these 8. And you're also going to be told what their new transformation position is on the final image. But once you have the final image, oftentimes, if this is working well, what it's supposed to be doing is actually overlaying. So you'll have maybe out of a single image, so out of image 1, maybe all of this right here, it's getting laid on top of the final image, and there has been no other image there before. But then I took an image and I had maybe this in the second image. So if I open up image 2, I've got all of this. Well, I need to figure out how to overlay this image onto this part of image 1. So here's where we get a little clever with that. We basically do a bunch of masking. First thing we do is we throw some assertions to make sure our shapes are correct. So we want to make sure that our width and heights are going to allow us to do this so the math doesn't break. Then what we do is we make an empty NumPy array of just all zeros. We make it the size of the first image, which should in theory match all of the images. And we just say, okay, there's nothing in you. We're going to have you be completely empty. Then we make a mask, which is just all of basically anywhere that there's a pixel information for image A and image B, we say that's the mask along with the given size. Then what we do is we say, okay, I want to create a submask that is only where there is image A pixels. So right here, we've got the image A, and then you say and not B mask. So basically this says, give me all of the pixels where there is pixel information from the first image, but not pixel information from the second image. That's going to give you just the A. And then we do the same thing with only the B with the second image. We say, give me all of the pixels where there is pixel or image data for image 2, but not for image 1. And then what we do is we do the combination. We say, okay, now give me the mask where those two overlap, so like the middle section. And what we do with that middle section is we basically say, what we do from there is we actually say, okay, I want you to take just the mask that only gave you pixel images for image A with no B. So basically if B is overlapped like this on image A, it's only going to give you from here over. It's not going to take the overlay or any of B. And say, okay, immediately just go fill that into that C mask that we made, that numpy. Because we know there's nothing to combine for those two, just send it. Then we do the same thing for B. We say, okay, there's nothing that this subsection of B is overlapping with, just put that right onto the C map. For this overlap section, though, what we got to do is we got to get a little clever. What we do is we want to kind of take feature sets from both. So we basically just do a transparency on both. We say, give me kind of half from A and half from B, and that's what these two are. So if you had, let's say for some reason you, in your program and in the use case of it, knew that your second image, you wanted to have much higher emphasis over the first image because maybe, I'm not sure, maybe for some reason your second image is going to be clear, or it's going to continue to be getting better and have a stronger relationship over your earlier images. You could drop that. You could say, okay, maybe give 10% to this guy and 90% to B. So you're going to have like 10% of A is going to be into that image, is going to be used, but 90% of image B will be used. For us, we assume that each image is going to be even, so we say use 50% from each. So which is why in the final image, you see a little bit of some overlap and blurring, specifically like maybe right there in the actual light post. That's because of this feature where there was overlap right here. So I said, oh, okay, I'm going to use from image A, but then I also have something from image B. So it needs to determine how it wants to overlay those. And at the end of that, we just return out the final fused image. That's the bulk of the functions. That is basically everything. The last thing you have is just putting it all together in a main call. So the first thing we do is we keep a list of all our basically processed images. Once we actually have produced the transformation for these images, so we took like image 2, and we've now wrapped it, and maybe it looks like it's a weird trapezoid, and it kind of shifted over. We basically just want to have a storage place for that. So I just keep a list of the actual processed, or I call them warped images. This right here is just starting off finding the initial. This is if we go to it. Remember, all it is giving it, we gave it hard-coded values. So this is just taking image 1 and putting it straight onto the final output image. We then take the homography, and exactly like I said, we just use what's called warp perspective. This is basically saying, okay, use this transformation matrix that I just gave you. Take this base image, so image 1, and warp it to match the new set points on the final image. So for image 1, all it's probably going to do is just scale it down. But for image 2, maybe we've got to do, you'll see when we do the production of it, you'll see maybe it needs to get kind of warped a little bit. Like you see this one overlaid, it got shifted. So this warp perspective is what actually does that and produces the new image that's kind of skewed like that. So then we just add it onto the list of images. Right here, all this is just iterating over for some name stuff. This is how you actually process where I kept the 0, 1, 0, 2. I did that naming. Then here I do a very dumb for loop, basically just in range. All you need to do to make this smarter is actually process how many files there are in this folder, and then you can just have a dynamic set. For me, I literally hard-coded the 8 images. Dumb, but super simple. We get the new file name using basically some string concatenation here. I read the prior image, which is for us going to be, if you notice I started 2, it's going to be image 1, so it's the first image. And then I get the next image. I get the next image that I want to actually map to this new relationship between the final image and the prior image. we detect two features. So the train one is detecting features on the current image, and the query is on the second image. The cool part about this detector algorithm is that it will find the same features without having a relationship to what was called prior. And what I mean by that is, if you look here, we call detect features on the current image with just the same, as long as we're using the same detector, without any information of the feature sets on the second one. It's smart enough that it will figure out, okay, this weird combination of pixels I'm going to call a feature. Oh, hey, I saw another weird combination of pixels that I consider a feature, and then you can go through and say, okay, oh, those actually match. So what you're able to do is just call detect features, and as long as you're using the same detector, if there's matching features, you don't have to do this between two images. You can do it between, or two images that are right next to it. You can do it between an image here and maybe an image I took 5 frames ago, which you'll see, which is why I took, I think, like image, I think it's literally image 5. Yeah, I went from image 4, I had gone over here, image 5, I went back, but it sees matching features between here, and it could also potentially find matching features between image 1 if you want to rerun it that way. That's what's really cool. So you pass in the image, you tell it I don't want to see the features, then you run a match. The actual match, this is the probably the thing you can tune the most in your actual detection. It's just saying, I've got these two feature sets, so orb is ran, but now I want to do the math on finding those. So remember, I said find 3,500 features on each image. Well, if we went through and processed how we want to match this feature with all 3,500 features, you've got this feature 3,500 times you got to check. This feature you got to do 3,500 times and check. What this does is these two lines here is basically an efficient way of actually processing through all the images or all the features and finding the top 80% of the matches. So right here, you basically do, it's called a BF matcher. And we use a norm function. So specifically I did the L2. If you look at this actual function, I'm not sure if I can actually go this way with it. Yeah, there's a whole lot of options. So it's the brute force matcher. So obviously not super efficient. But there's a lot of options you could actually do to kind of tune this and tweak it. Specifically, you can give it different actual functions that you want to use to actually do the matching. So I did the L2, you could also do the norm L1 and a bunch of other options. If you actually go and look at the documentation for this, you can read more information about the pros and cons of all of these. I think the norm Hamming 2 is also a really good choice. That's a whole world of computer vision that if you want to, again, really dive into this, I highly recommend you go down. Then what we do is we say, okay, like I said, we want to find only stuff that is the top 80% of matches. So we actually basically assume out of 3,500 matches that not all of them are going to be perfect. And if you include all of them, those bad matches can actually start to hurt your transformation and hurt how you're actually mapping one image to the other. So you only want to kind of take like the top percent. If you were getting pretty bad matches, this is one of the first things I would do to tweak, is actually drop this number. So I take 80% of them. Maybe you only want to take 50%, or maybe you want to say I take the top 10% of matches. The trade-off there is that usually you have to provide more features to do. 3,500 is plenty, so I could drop this down to 10%. But if you're only operating with, say, 10 features or 100 features, and you suddenly throw 80 of them, that's a huge chunk that you're getting rid of and saying, okay, I really am counting those 20 to be super accurate. So there's a trade-off there. If you have high compute power, you might as well throw a bunch of features at it and only take the top 20%. If you have low compute power, you got to start to make trade-offs and say, okay, I want to take like 80% of it, but let's only run features for 100 or 200 features. It's that kind of game you got to play. Then we just append them all to the valid index or the valid array. And from there, we just pass in both the actual points, basically it was the source and destination information into the find homography transform. And from there, we've got a homography that gives us the second image mapped down to the first image, which itself has already been mapped onto the final image. From there, we do a dot transform, which is basically just to run through and map that onto the final image. So these two steps just accomplish what I had mentioned, which is taking your first image, mapping it down to the second, your second image, mapping it down to the first, which has already been itself mapped to the final. From there, you do a warp perspective and throw it on there, and then you just append the final little tilted image. Basically right here, these 4 steps are what gets you an image that actually goes from this one up here, finds a relationship to this one down here, and then we'll adjust and rotate, shear, and remap onto the final. This is kind of the whole chunk that goes between the 2 images and finds their match. Then we just update some local variables to track it. So we say, okay, this is now the previous, and then we jump to the next file name. Then to actually construct the final, we do a similar concept we did with the overlay stuff. We build just an empty array of all zeros, so there's no information in there, of the width and height that we constants that we set up above. We give it a dimension, we say it's just RGB, and then we just give it a type. So it's unsigned int 8. Again, you can play with all this. All of our images, I believe, we process with the UNA8 unsigned int 8, so there's no point adding extra information there. It's just going to be empties. And then you say, okay, for every image that we've just basically found this transform for, we haven't stitched them together yet. What we have is we know exactly how they should get overlaid, but they're all individual images right now. Maybe this one looks like this one looks like this. We know they all need to go on top of each other. At this point, you just run the fuse color images function that we talked about, which does the math between, okay, there's nothing here, there's nothing here, we'll lay those over, you got overlay, let's make 50% of each one of those. And then we just do some im show to kind of see the process getting built. We make the final window, and we show the final image. That's it. And then we write it out to an image called final personal, which is what you saw in the beginning. You see the black space, but you see how it overlaid and mapped really well. At that point, that's it. So if we run this one more time, it's going to go through. It'll find the transforms for each image, so it's not the fastest thing, but it's finding 3,500 matches between each. And then you can see it slowly iterate over. So here's the first one. This is the first image I took, and it's getting mapped over. And this is the kind of window, so you can see you can actually drag it around. It's got a little X button. It's actually like a full window. If I hit enter, it's going to take the second image, and it shows you. So here is the image C, if you remember in the function on the actual fuse. It's this guy. It's the overlay between the two. If I rerun that, it's got the next image. But here is the final overlay. It's getting constructed piece by piece. So you see this image has actually like some shear to it, and it's got a little bit of rotation. All of that is what got found by the homography transform. And this right here, where it actually overlays, it's what's getting done by basically these final steps right here, where you actually map it on top of each other. So if we go back to this guy and this guy, just keep hitting enter, what we'll see is you see each image individually, and you see how it builds on top of the final mosaic, or rather the panoramic. And boom, then you produce your final image, saves out, and you're all done. So if I close these guys, if I hit enter, ta-da, that's it. So I hope you enjoyed the tutorial. I know it's not like the most in-depth one, but I just want to do a quick little programming thing. Mainly because this has been a cool project to build on top of future stuff. So I've got some projects coming out, like with the Segway, that's going to do a lot of the visual odometry stuff. And I wanted to give some, even just a rudimentary intro to how we might do some orb detection and the actual transformations between 2 frames, which is what lets you build an actual full map of the environment frame by frame. So if you liked it, please make sure you subscribe, give it a like, comment below. Yeah, I'll see you guys on the next one. Thank you so much. Have a good day.